For a period of time in the 1960s, a research team was trying to develop a perfect conductor. The theory was that if they could grow perfect crystalline metal wire, there would be no signal loss and therefore no errors in communication. And they succeeded in creating the perfect wire. However, when they tested it, sometimes there were still errors. Do you know why? It's because we live in a quantum mechanical universe, and the location of electrons moving down a conductor is probabilistic. So occasionally an electron will appear outside of the wire and get lost. Errors are going to happen. Loss is going to happen. So the challenge isn't to avoid it, but to accept it and deal with it. In this lesson, you'll learn about designing systems to handle failure caused by loss of resources.
So let's start here with failure due to a loss. Now, failure due to loss of resources required by the service, a single point of failure, and correlated failures. These are the different scenarios we want to cover. So remember this. Failure is not optional, it's mandatory. Hardware, software, people, communications, it's all going to fail. This is why we came up with our processes and best practices to try to get around some of these things. Don't depend on hardware. Make sure that you create modular software that you monitor. You can do testing, canary testing, a number of different ways to ensure that at least your customers don't have to experience the pain of any bugs or issues. People, right? You're always going to have to review procedures and understand a proper escalation path. Finally, communication. Don't assume that somebody else has sent it out. You have to have a design process that communicates with your customers, other team members, and important people who are going to be potentially affected or need to learn from this. Because remember, the internet itself is designed to route around failure. So why don't you design your applications the same way? So here's our takeaway. Anticipate failure, design for failure, and fail gracefully. So let's start with single points of failure. Right? In this case here, single points of failure could be anything. It could be hardware. It could be multiple machines failing at once because they're attached to the same power supply, power source. You could have a network paths that could go down. You probably all heard the situation where a backhoe has dug up fiber cables. Or in one situation, I actually worked with a customer in which somebody broke into their data center and literally took a hammer to everything they could find. They took a screwdriver and were stabbing out all of the individual network ports. I mean, they did anything they could, and they clipped all the telco and fiber going into the building. So there were ways around this, right? Having a replicated data source outside of that small little data center that they have, which meant data replication. In fact, if you have the data, pretty much everything else can come online. Now, fortunately for this customer, we did have replicated data copies, and they did get a hold of one, but the second one managed to survive. So here's the goal: replicate everything. So some beautiful towers here in Kuala Lumpur, if you're ever looking for a nice place to visit. Second, design to avoid single points of failure. Right? This is huge. Now, what we also like to design for is a spare for the spare, so N+2, because you want to plan to have one unit out for upgrades or it failing, and another one survives while it's failing. This is the whole thing. What oftentimes is you could take down one machine for maintenance, but what if another machine also fails? And that's the N+2. Now you start to get into some very high-level statistics on whether that would actually occur. That's why N+2 is a pretty good ground rule to stick by. So don't make any single unit too large. That's why we've been focusing on microservices. Don't concentrate responsibility onto a single processor server. Again, where's your single source of state? Is it going to be in a distributed, replicated manner? And try to make units interchangeable clones. This is huge. Microservices let you do that. Containers let you do that. Different modules in Google App Engine let you do that. So this way you can simply clone these applications, throw it on any piece of hardware, even fail over to another cloud provider if necessary. Correlated failures. Now, we've all seen this happen. This is when something fails and it causes a huge chain of events. You can see a number of different issues here, right? If a zone or region is lost, all the resources in it fail. You've heard the analogy about an airlines. All it takes, I remember just flying recently, they were preventing planes from coming into Seattle, from leaving from wherever they were coming from. So there were some planes that got there, were circling, some couldn't even leave their destinations, caused a huge chain of effect across the West Coast. So a group of related items that could fail at one time is called a failure domain. So really think about what could happen. And I remember working with some customers when I said, hey, look, we can build resiliency if these servers fail. And they said, you know what, we're going to think bigger. Our failure domain is the entire rack. If that APC unit goes out, or if we lose the top of the rack switch set, even though they were in pairs, we want to be able to survive the failure of an entire rack. So you define what your failure domain could be that could create that potential single point of failure or a correlated set of failures. So in this case, we want to design to avoid correlated failures. Now, doing that, it's easier said than done, but in the best practices around this are dividing business logic into services based on failure domains. So understanding if that failure domain could occur, how do I recover from it? So not just individual components, but entire failure domains. It makes it a little bit easier to look at it from a bigger picture. Separating and isolating the risk, and design independent but collaborating services. So microservices that are independent but they can't communicate, and you have failover mechanisms in case that workflow logic tends to fail.